Okay, let's unpack this. Imagine picking up your phone, maybe chatting with an AI, and then you read this really bold claim that the AI models powering these interactions, the ones writing code, generating images, they fundamentally lack reasoning ability.
Yeah, not just like struggle sometimes, but fundamentally lack it.
Exactly. And that assertion came from researchers linked to Apple in a paper called The Illusion of Thinking.
And they were specific too. They tested what they called large reasoning models, the big names, DeepSeek, OpenAI's O3, Anthropic's Claude on these complex planning
Almost like
puzzles.
Tower of Hanoi?
Right, Tower of Hanoi, river crossing problems, that sort of thing. And they reported seeing this accuracy collapse. The models did worse as the puzzles got bigger.
And their conclusion was
That the models weren't truly reasoning, it was just an illusion.
that's quite a statement, especially coming from Apple, right? A huge player.
Oh, definitely. It kicked up a lot of dust online. Lots of debate, speculation about, Apple's own AI ambitions maybe playing a role.
But here's where it gets really interesting. The sort of main counter-argument didn't come from another human team initially.
No, it came from one of the AIs that was criticized, Anthropic's Claude Opus model.
The AI itself wrote a rebuttal.
Well, it acted as the lead author on a direct response paper, and the title was, honestly, pretty brilliant.
Oh, what was it?
The illusion of thinking.
The illusion of thinking. Wow, that's almost like AI looking in the mirror.
Kind of, yeah.
So our mission today in this deep dive is to get into that rebuttal paper from Claude. What did it argue? What does it tell us about Apple's claims, but maybe more importantly, about how we should actually test these AIs?
Okay, so Apple's paper, Illusion of Thinking, definitely set the stage with that accuracy collapse claim. Generated a lot of buzz, as you said.
Right.
But Claude Opus's response comes right back and says, hold on, the reason you saw that collapse isn't necessarily a flaw in the AI's reasoning.
Oh, so what was the reason, according to Claude?
The core argument, the central thesis, is that the collapse is mostly down to problems with the test itself. The experimental design Apple used had some significant flaws and limitations.
Okay, so it's not the student, it's the exam. That shifts things quite a bit.
Exactly. Claude's paper points out three main issues with Apple's methodology.
Let's break those down. What's the first one?
So the first big one is about practical limits, specifically output token limits, and how Apple's evaluation didn't really handle them well. This showed up clearly with the Tower of Hanoi puzzle.
The one with the discs and pegs moving them across? Classic.
That's it. Now, Apple's test required the model to output the entire sequence of moves, step by step, start to finish.
Okay.
But the thing is, the number of moves for Tower of Hanoi, it grows exponentially with the number of disks, n. The source material even mentions calculations showing the output length needed just explodes. It's roughly proportional to the square of 2 to the power of n.
Exponential squared. Okay, yeah, that gets huge fast.
Incredibly fast. And models have limits on how much text they can spit out in one go their token limit. Maybe 64,000 tokens, maybe 100,000, depends on the model.
Right.
So if you ask for the full move list for, say, N15 disks in Tower of Hanoi, the number of steps is enormous, way more than the token limit.
So the model literally can't list all the steps, even if it knows them. It would just get cut off.
Precisely.
Huh.
And this is the crucial part Claude's paper highlights. They found evidence, even looking at examples like tweets mentioned in the source, that the models often know this.
They know they're going to hit the limit.
Yeah, they might output something like, okay, I see the pattern, but listing every single step would make this response way too long, so I'll stop here.
Wait a minute, that's completely different from saying, I don't know how to solve it. The model is saying, I can solve it, but I can't write it all down for you.
Exactly. And Claude argues Apple's automated scoring system just wasn't sophisticated enough to tell the difference. If the output wasn't the complete, exhaustive list, character for character perfect, it was marked as a failure. It couldn't distinguish hitting a token limit from actually being unable to reason through the problem.
So the evaluation was too rigid. It penalized the model for a practical constraint, not necessarily a lack of logic.
That's the argument. It misclassified the behavior.
So the takeaway for evaluating AI here is we need tests that understand these system limits, like output length.
Definitely. You can't just assume infinite output. The test needs to separate the model's understanding from its ability to type out, thousands and thousands of steps under constraint.
Okay, that makes sense.
Yeah.
That's issue one, rigid evaluation, ignoring token limits. What was the second big problem Claude flagged?
This next one is pretty stunning, actually. It involves the problems themselves, specifically in the river crossing tests, like those missionaries and cannibals variants.
Ah, yes, getting everyone across the river safely. Tricky stuff.
Right, so Apple tested versions with N actors, say N missionaries and N cannibals, and a boat that could hold 3 people. Claude's paper points out, citing existing mathematical proofs, that the specific versions Apple used where N is 6 or more, with that boat capacity of 3, they're mathematically impossible to solve.
Wait, impossible, as in there is no solution.
No solution exists for N greater than 5 when the boat size is 3. That's a known result.
So Apple was testing the AIs on puzzles that literally cannot be solved.
That's what Claude's paper asserts. And because the puzzles were impossible, the models obviously couldn't provide a solution path.
And the evaluation marked them down for failing.
Exactly. They were scored as failures for not solving unsolvable problems.
That's like failing a student for not finding the answer to 2 + 2 = 5.
The paper uses a similar analogy, yeah. Like penalizing a logic solver for correctly saying a formula is unsatisfiable, meaning it has no solution. The AI was essentially penalized for identifying, or at least failing to find, a solution that doesn't exist.
Wow, okay, that seems like a pretty major oversight in the test design itself.
It really highlights a danger. Purely automated evaluation, just checking if the output matches some expected final state, can completely miss fundamental properties of the problems being used.
So the principle here is you have to actually check if your test questions are valid. You have to validate the test itself.
Absolutely critical. Verify solvability.
Yeah.
Don't just assume your puzzles work, especially when you're using them to make big claims about reasoning ability.
Right. Okay, so we have token limits leading to misinterpretations and testing on impossible puzzles. What was the third issue?
The third one is about how Apple measured difficulty. They used something called compositional depth, which basically just means the minimum number of moves in the shortest correct solution.
Minimum moves. Okay, my first instinct is, yeah, shorter solution probably means an easier problem, right? Longer solution, harder problem.
It sounds intuitive, doesn't it? But Claude's paper argues that solution length is actually a really poor way to judge the true computational difficulty, how much complex thinking or searching is needed to find that solution.
Okay. How so?
They use the same examples. Think about Tower of Hanoi again. The solution has tons of moves, like 2 to the n-1, exponentially many.
Right, we established that.
But the decision at each step is super simple. There's a clear, simple, recursive pattern. Move the top disk here, then recursively move the stack. It's O1, complexity per move decision. Lots of output, but simple logic for each bit.
Okay, so long list, but easy steps.
Exactly. Now contrast that with river crossing. The solutions are much shorter, maybe only like 4 times n moves.
Fewer steps. So Apple's metric would say it's easier.
Right, based purely on length, but finding that short path is way harder computationally. You have all these constraints: who can be left with whom, boat capacity you have to explore a complex state space, backtrack, maybe do a tricky search. The problem class is NP-hard. It requires much more sophisticated reasoning per step, even if the total number of steps is smaller.
Ah, okay. So river crossing, short solution, but requires complex search and planning. Tower of Hanoi, long solution, but follows a simple, repeatable pattern.
Precisely. So using just the solution length, the compositional depth, as your main measure of difficulty is misleading. It doesn't capture the actual reasoning or search complexity involved.
And Claude suggests this explains some of Apple's results, like why models might seem okay on Tower of Hanoi sometimes, but fail on river crossing.
That's the idea. The metric was flawed, so the conclusions drawn from it about relative difficulty or where models fail might also be flawed. It wasn't measuring the right kind of hard.
So it seems like across the board, output limits, impossible problems, bad difficulty metrics. Claude's argument is that Apple's test setup was the problem, not necessarily the AI's core ability to reason.
That's the central thrust of the rebuttal, yes. And importantly, they didn't just point fingers. They ran their own tests to show how changing the evaluation reveals different capabilities.
Oh, what do they do?
They went back to Tower of Hanoi, specifically N15, which is one of those sizes where Apple's results suggested failure because the full move list is just too long.
Right, exceeds the token limit.
But instead of asking the model to type out all 32,000 plus moves,
They asked for something else.
yes, they asked the models to output a short piece of code, specifically a Lua function, that if you ran it would print the sequence of moves.
Ah, so asking for the algorithm, the recipe, not the fully executed output.
Exactly. Asking for a compact representation of the solution logic.
And what happened?
The results were striking. Across several top models, Claude 3.7 Sonnet, Claude Opus 4, OpenAI o3, Google Gemini 2.5, they found very high accuracy. The model successfully generated the correct Lua function.
And how long was that function token-wise?
Crucially, under 5,000 tokens.
Wow. So under 5,000 tokens to provide the logic for an N15 solution, compared to needing potentially over 64,000 tokens just to list the steps.
It's a massive difference, and it strongly suggests, according to Claude's paper,
Yeah.
that the models do understand the recursive algorithm. They have the reasoning capability.
They just couldn't demonstrate it when forced to use an extremely verbose output format that hit system limits.
Precisely. The failure wasn't in reasoning. It was in the mismatch between the task demand, exhaustive enumeration, and the practical constraints, token limits, combined with an evaluation method that couldn't see past that.
Okay, this whole back and forth, Apple's paper, Claude's rebuttal, it's fascinating from a research perspective, but why should this matter to, you, our listener? Why care about this academic debate?
Well, it's not just academic, is it? This is about how we understand the real capabilities of these increasingly powerful AI systems that are showing up everywhere.
Right, they're in our phones, our search engines, our work tools.
Exactly. So how we test them, how we evaluate what they can actually do, that directly shapes how they're developed, how they're used, and frankly, how much we trust them or what we expect from them.
Are we using the right rulers to measure them, or are our rulers kind of broken, giving us misleading readings?
That's the core question this debate raises. Are we accurately gauging AI intelligence, or are our methods flawed, potentially making us think AI is less capable than it is, or maybe even missing where the real limitations lie? It forces us to scrutinize our own evaluation techniques.
So if we pull it all together from Claude's perspective, what's the main takeaway here about evaluating AI reasoning?
The argument is that Apple's results did highlight some real-world engineering challenges. Things like token limits are real constraints, evaluation needs to be robust, understanding the properties of the test problems themselves is vital.
Okay, so those are real issues.
Yes. But Claude argues these issues don't actually provide strong evidence for a fundamental lack of reasoning in the models. The observed failures were more likely artifacts of the test setup.
The intelligence might be there, but the test wasn't designed well enough to let it shine through, or it misinterpreted the results.
That's the essence of it. And this leads to some concrete suggestions for how we should evaluate AI going forward.
Like what?
Like designing tests that specifically separate reasoning ability from output constraints. Like always verifying that your test problems are actually solvable.
Seems basic, but apparently necessary.
Right. And using better metrics for complexity, ones that reflect computational difficulty, not just output length. And being flexible, considering different ways models can show understanding, like outputting code or algorithms, not just raw step-by-step lists.
So it's a call for more sophisticated tests to match these increasingly sophisticated AIs.
Exactly. We need better tools to understand what's really going on inside these systems.
And the paper, Claude's paper, apparently ended with a pretty thought-provoking line.
It did. It really sums up the core issue.
What was it?
The line is, the question isn't whether LRMs can reason, but whether our evaluations can distinguish reasoning from typing.
Oof. Whether our evaluations can distinguish reasoning from typing.
Right.
That really...
Yeah, that hits hard. It puts the focus right back on us, the humans doing the evaluating.
It makes you stop and think about everything we see in AI do. Are we seeing as actual cognitive limits, or just the limits imposed by how we ask the questions and how we measure the answers? Are we testing thinking, or just output generation under constraints?
It's a fundamental challenge. How do we truly know what these systems understand versus what they can parrot back in the format we demand?
A critical question to keep asking as AI gets woven deeper into our lives. Well, thanks for walking us through this fascinating deep dive into how we test AI thinking. Definitely gives you something to chew on.
Absolutely. It's a moving target.
Until next time, keep thinking.